Eccentricity literally means being off-center. It can occur if the coupling is not bored in its physical center, or if the bore is bigger than the shaft, and the set screws pull the coupling out of center. When measuring runout, the dial indicator is mounted to a fixed point in space. If the coupling is disconnected, attach the dial to the shaft opposite the one you want to check. Or if the coupling is connected, you can use the mag bracket to mount the dial indicator to the base of the machines, or any other fixed point in space. We recommend that you first check for runout at the hub, or rim, of the coupling, because there you will pick up both eccentricity and bent shaft. Some people will also measure runout in the axial direction, which, in addition, would tell you if the coupling bore is skewed. Before taking the readings, make sure the dial is mounted perpendicular to the shaft. Set the plunger to half its travel range to assure both negative and positive capacity. Once the dial is affixed, rotate the shafts. Make sure you rotate in only one direction. Find the greatest distance from zero in either positive or negative direction. Stop rotating the shafts and reset the dial to zero. Now, continue rotating the shafts and watch the dial for the maximum amount of change, which equals the total amount of runout. If the runout is within acceptable limits at the hub, 2 thou or less, then the coupling must be bored properly enough and the shaft is reasonably straight and within acceptable limits. In this case, the dial is indicating excessive runout of 22 thou. When excessive runout is observed, we next need to determine if it is being caused by a bent shaft or by an eccentric coupling or both. We achieve this by repeating the same measurement process at the shaft. You'll want to take the measurement as close to the coupling as possible. In this case, there is 21 thou of runout at the shaft, accounting for most of the 22 thou of runout we observed at the coupling. Therefore, the bent shaft is the problem. If our measurement at the shaft had been close to zero, the problem would have been eccentricity of the coupling. Of course, we could observe a situation where both conditions occur, a bent shaft and an eccentric coupling. If excessive runout is present, it should be corrected before attempting precision shaft alignment.
The current centrifugal compressor's anti-surge protection systems give a limited vision of operative parameters and their related conditions of danger. A vision limited on a particular fixed reference status. Limited because it does not foresee effects of possible variations in chemical gas composition. Limited because it does not forecast the consequent change of the compressor behavior when it works out of its reference conditions. These systems base every evaluation necessary for the protection from surge on an approximate relation among some main operative parameters, a relation that is considered fixed and invariable. But in severe applications and in conditions of variability of inlet parameters, such as gas mix composition, inlet temperature, or inlet pressure, the current systems may not be able to assure the adequate protection from surge. IPC introduces SPS, a sophisticated control and protection system with a different vision. SPS is able to respond in real time to every process parameter's variation. By using sophisticated thermodynamic theories, advanced algorithms for compressor modeling and vibration monitoring, ensuring the total compressor protection. Furthermore, thanks to innovative auto-diagnostic logics, SPS is able to check the proper compressor functioning and to detect possible machine degradation. SPS, the most innovative system for total anti-surge protection. The future is now.
Atlas Copco multi-stage centrifugal compressors use integral gear technology, the industry's most compact and efficient turbocompressor design. Our integrally geared compressors are reliable, energy efficient, and specifically optimized to your process requirements. Integrally geared compressors deliver multiple speed capability by placing rotors on separate pinions. Each compression stage runs at the optimum speed for high efficiency. Compressor bearings and gears are lubricated by the main lube oil pump, which is driven through the bull gear for reliable oil flow. The compression process begins with gas entering through adjustable inlet guide vanes, or IGVs, which are standard on all Atlas Copco compressors. IGVs control how much flow is sent into the machine, providing accurate process control. With IGVs, compressor efficiency can be increased by around 9% versus other inlet assemblies. Our impellers, available in open or closed configurations, impart kinetic energy to the gas. This is turned into pressure in the diffuser and then the volute. Gas temperature rises during the compression process. To improve compression efficiency, interstage cooling can be easily accommodated between any of the compressor stages. Atlas Copco offers a range of intercoolers that are precisely matched to process requirements and meet all relevant international standards. In the configuration shown, water coolers are available in either water in the shell, gas in the tube, or gas in the shell, water in the tube designs. High-speed rotors are supported by radial tilting pad bearings that eliminate virtually all vibration while providing superior rotor stability and smooth rotation. Depending on the application, this can be a combination of radial and thrust bearings. The bull gear shaft rotates on multi-lobe sleeve bearings. Compressor sealing options may include dry gas seals, floating carbon ring seals, and labyrinth seals in various combinations and arrangements. Our range of integrally geared compressors is used in a variety of industries, and our compressors can be customized for a specific process. As the name suggests, all compressor stages of integrally geared compressors are mounted on one gearbox. Thanks to their rotor and aerodynamic design, along with intercooling capability, integrally geared compressors are more efficient than other rotary compressors. To enhance performance, a number of other features are available, such as variable diffuser guide vanes, or DGVs, which can be added to complement impeller aerodynamics. Adjustable DGVs enable larger turndown, which ultimately results in wider process control without impairing efficiency, an ideal mix that is increasingly required by process designers. Both variable inlet and diffuser guide vanes provide stable compressor operation over a wide range of conditions at a constant discharge pressure. To control gas temperatures during compression, in situations where cooling water is not easily accessible, an air-cooled version of our compressor is available. For applications where process gas leakage is restricted, or when process gas needs to remain within the system, our integrally geared compressors can be built with dynamic dry gas seals. These seals can be supplied in single, double, or tandem arrangements, depending on the application. In fact, Atlas Copco was the first compressor manufacturer to implement dry gas seals on integrally geared compressors, packing efficiency, high machine availability, and superb process control onto a small footprint, Atlas Copco integrally geared compressors give your process the extra edge in a variety of applications across many industries.
The axially split casing design allows removal of the impeller and bearing housing assembly without disturbing suction and discharge piping. Storage and protection. All pumps are shop tested and ready for operation when delivered. If equipment is to be stored for long periods of time, 6 months or more, should be kept in a clean, dry area, and the following precautions should be taken to ensure that the equipment remains in good condition. Be sure that the bearings are fully lubricated. The shaft should be rotated 10 to 15 revolutions by hand periodically in order to spread the lubricant over all the bearing surfaces. Suitable intervals are from 1 to 3 months. Installation. The pump should be located as close as possible to the liquid supply so that the suction line is short and direct. Location should require a minimum of elbows and fittings in the discharge line. Before installing the pump, ensure that the foundation on which the pump will be placed is prepared well. It has to be sufficiently substantial enough to take the weight of the pump and absorb any possible vibrations from it. The foundation has to be absolutely straight, without any inclination or tilting on any side. The foundation bolt of proper size should be embedded in the concrete and base plate tightened, ensuring that it is level in all directions. Piping associated with the pump must be anchored and supported independently of the pump and should never put any strain on the pump casing. When the pipes are not supported, their weight is borne by the pump casing and may cause them to crack or deflect. It is important that the connections be carefully aligned axially, angularly, and in length. Suction piping in case of static suction lift condition, negative suction. The piping run and the connection fittings should be properly aligned and supported separately. The elbow should be of long radius type. All suction piping must be airtight. The suction pipe should be sized to ensure the liquid velocity of not more than 2 meters per second. All suction pipes should have a continuous rise to the pump suction inlet. 6 mm per 100 mm slope is recommended. The recommended suction pipe size should be at least 1 commercial size larger than opening of the pump inlet. No isolation valve is recommended. There should be a tapping provided for installing a vacuum gauge in suction line. The reducer joining the straight length of the pipe in the pump line should be an eccentric reducer, with the inclined side of the reducer as the bottom side. The straight length of the pipe after the eccentric reducer should be 2 times of the pipe diameter. The suction strainer must be at least 4 times the suction pipe area, and the mesh sides should screen out solid particles that could clog the impeller. The minimum depth of submergence of the strainer should be at least 4 times the pipe diameter measured from upper row of holes of strainer. The distance between the bottom of strainer and the floor of the tank should be considered as 2 times of pipe diameters. A stream of liquid falling into the pump near the intake pipe will turn air into the liquid. The supply line should extend down into the liquid. A short elbow should never to bolt directly to the pump's suction nozzle. The disturbance in the flow caused by the sharp bend so near the pump inlet may result in noisy operation, loss in efficiency and capacity, and heavy end thrust. If separate suction lines cannot be used for each pump, then a tapering header with Y branches should be used. A straight branch header should never be used. Suction piping in case of flooded suction condition. Positive suction. In case the water is being supplied to the suction through gravity, example, an overhead tank, a slightly different setup is needed. The elbow should be of standard type or of the long radius type. Isolation valve should be provided in suction line. The pipe supplying from the tank into the pump should have a descending inclination. The straight run of the piping leading to the pump suction nozzle should be at least 3 times to 6 times the diameter of the pipe from the upstream elbow. The suction pipe should be sized to ensure a liquid velocity of not more than 3 meters per second. There should be a tapping provided for installing a pressure gauge in suction line. The reducer joining the straight length of the pipe in the pump line should be an eccentric reducer with the inclined side of the reducer as the top side. Stuffing box seal connections are usually made from the top of the pump casing. If the liquid being pumped is unsuitable for sealing, then it is preferable to bring fresh, cool water to seal connections from an outside source. Centrifugal separators or other filters may be used to remove abrasive particles from the liquid being pumped if an outside source is not available. Description of the discharge pipe. The piping run and the connection fittings should be properly aligned and supported separately, reduce strain on the pump casing. There should be a pressure tapping as close to the pump outlet and before the isolation valve as possible to measure the pump shutoff head. Concentric reducers are installed in the discharge pipe to minimize friction losses. The check valve used in the discharge should be of non-slam type to prevent reverse flow and protects the pump from excessive back pressure. The isolation valve is provided downstream of the check valve so that these can be taken up for maintenance, priming and starting whenever required. The recommended discharge pipe size should be at least one commercial size larger than the opening of the pump outlet. The number of fittings and size changes should be minimum to prevent fluid friction losses. Expansion joints may be used only after a careful piping analysis, especially when the discharge pressures are on the higher side. Installation of pump and prime mover. The pump and motor unit needs to be fitted firmly onto the base frame using nuts and bolts before fitting in any pipes. It is essential to confirm the distance between the shaft ends. In the subsequent step, the pump and motor are aligned to the final tolerance using a reverse dial gauge or a laser alignment tool. After the alignment is completed, the piping associated with pump should be bolted. Once this is completed, the alignment should be rechecked and similar readings should be obtained. If this is not the case, then the piping should be investigated and suitable corrections should be made. If this is left unattended, it can cause stress on the pump casing. Misalignment may be the cause of noisy pump operation, vibration, premature bearing failure, or excessive coupling wear. Once the pump and motor have been coupled, test the movement manually by rotating it by hand to see if it is rotating smoothly.
Here we have a pump trainer. We have an electric motor with a horsepower meter through a magnetic coupling to a centrifugal pump. The pump itself is made of acrylic, so we can see the spinning impeller inside. We can also see the fluid go through. It's got a gate valve here on the discharge. It's got another valve over here on the suction. And all the piping here is clear, so we can watch the flow of fluid. But right now it's all clear water, so we can't see much in that regard. It's got a rotometer here showing us the amount of flow. But what I'm going to demonstrate here is cavitation. We're going to purposely cause cavitation to occur in the system. We're going to do so by keeping the discharge valve wide open like it is and pinching off the suction valve. What that will do is reduce the pressure in this line, and you'll see this compound gauge show a stronger and stronger vacuum as we begin to pinch off this valve. Now start to turn this clockwise, and you'll see the gauge's indication go down. You'll also begin to hear cavitation take effect, and we'll be able to see the bubbles form inside of here as it cavitates after it flashes in the vapor and cavitates into liquid again here. So here we go, closing the valve. And watching the gauge. The gauge will go down. Minus 10 inches of mercury. Minus 12, minus 14, you can start to hear flashing occur there. 16, more noise. Minus 18, minus 20. You start to hear that sound that sounds almost like rocks going through the pipe. There's no debris, there's no solid material through here. That solid sounding sound is really the collapsing of the vapor bubbles as they go back into liquid form. You can really hear it now. You can see it occur inside of here. It's a very pronounced action and noise. As the water goes through the valve, it reduces pressure going to the restricted valve. Its pressure drops below the vapor point of the water at this temperature. It flashes into steam, and then after it comes out of the valve and expands again, the pressure goes up. And what happens is those vapor bubbles collapse back into liquid. And that's when we get the cavitation effect. We can see it happening here. We can also see some bubbles here in the scroll casing of the pump. Cavitation is very destructive, especially upon metal surfaces. The acrylic surfaces here seem to handle it a little bit better, but with metal surfaces there's no give, and it's very destructive. The metal will become pitted by the high pressure jets formed by the collapsing bubbles. So I just want to illustrate what cavitation looks like in an acrylic tube and what it sounds like. It sounds like rocks, literally like rocks going through the pipe. And again, we cause it by dropping too low of a pressure, causing flashing to occur, and when the pressure rises again, the bubbles collapse, and that's when cavitation occurs. I will open this valve back up. That increases the pressure on the suction side of the pump, less and less vacuum, until we no longer flash and we no longer cavitate. And that's a happy pump.